Howdy, this is Plate Techtonics 4.1. So let's talk about the crust first. The crust contains, we've got 14 of these tectonic plates.
It's kind of like if you were to fracture a boiled egg, very similar looking thing. And when we see volcanic activity or when we see earthquake activity, it is happening at these plates, which is very important most of the time. Sometimes it happens other places, but most of the time it's happening due to the motion of those plates.
Now, all of you have learned this before, most likely back in middle school, but our Earth is divided into four main sublayers. We have our inner core, our outer core, our mantle, and our very, very thin crust.
Now, our core is solid, and it's primarily composed of iron, nickel, and other heavy metals. Uranium is one of those heavy metals, and all of those heavy metals are going through radioactive decay. And because they're going through this radioactive decay, they're releasing so much heat. So because of all this heat that's released, this core is super hot. It's actually hotter than the surface of the sun in here. Extremely hot, which is causing the melting of everything around it. Now, our inner core is solid. Our outer core, however, is liquid. And the swirling eddies, we have a lot of these swirling eddies that exist because of the density changes from our inner core to our outer core, which create these swirling eddies. And these swirling eddies are what cause the magnetic fields on this planet. The largest part of Earth is our mantle. Very similar to the composition of oceanic rocks. It's going to be like a semi-solid, flowing slowly, like a thick liquid. I like to think of this as kind of like toothpaste, a little bit like the gooiness of toothpaste. And that gooiness is very important,
because it's going to help drag the plates on top of it, causing them to move as well.
So think of this like ooey gooey toothpaste that is moving all throughout our mantle. The crust is the outer thin layer, very important, thin outer layer of solid and brittle rock. Some areas that are continental crust where we have mountains, they're a lot thicker, like 70 kilometers.
Other areas are very thin, like the oceanic crust. But I want to focus on one of the biggest things here. Sometimes you're going to use the word crust, but sometimes you'll also see the word lithosphere. And kind of all of this, including the upper mantle, is often called the lithosphere. It's a combination of those two. Now, in the mantle, we have kind of the crust up top here, which is super cold. And then we have the mantle down below, which is close to the outer core, which is extremely hot. And these differences and changes here, if I have very hot material, then it's going to start vibrating more. And when it starts vibrating more, it's going to become less dense. And when it becomes less dense, it's going to rise. Then it's going to hit the colder crust up top, lose that heat, become more dense, and come back down. So it creates these currents of upward and downward movement of this toothpaste-like fluid when it's heated. And in this process, we can get a little bit of dragging happening on the crust. Same idea here. We come up, we've got hot material, it becomes less dense, so it moves up. Then it cools, becoming more dense, so it comes back down. This is what the convection currents are. We see it in the mantle, but we also see it in the air when it comes to weather as well.
So as I mentioned, it's these convection currents in the mantle that are going to drag the crust along with them. So the particles heat up, they rise, they grab some of this crust and they move it this way. In other areas, same thing. Heats up, moves up, grabs some of that crust and moves along this way as well. So that's why our plates move. It's because of these convection currents in the mantle that are dragging those plates.
Now, what we can see sometimes is I have a convection current going this way and another convection current moving in that direction. So this plate is gonna head that way, this plate's gonna head that way, and we have this spreading center. So the crust is gonna split, and then this magma is gonna go up and it's gonna kind of fill in the cracks in between. This is what we call a divergent boundary. We're gonna look at those a little bit later, but it's an example of where this spreading is happening when these plates are pulled apart from each other. Now, the spreading centers, when we have this spreading, it creates two things. It creates ridges if I'm in the ocean, and it creates rift valleys if I'm on a continent. So here's an example. In my ocean, I have, again, we're moving this direction, this one's moving that direction. They're pulling apart, and so the mantle is going to come up and it's going to fill in this area here. And what you see a mid-ocean ridge that's forming in that spot. On land, this is happening, and we're actually creating like an ocean. So these two are being pulled apart.
And this area here, we have this water is going to get bigger and bigger and bigger as these pull apart from each other. This is actually where Kilimanjaro is, massive mountain, because it's on one of these plate boundaries.
So here's an example of the seafloor splitting if it were to happen in an ocean. Here's our plate moving in the different directions. And so the magma is going to fill this new land in here. So we're going to get new crust forming in this section here. Now, over 1 million years later, the crust that used to be here is now here. It's moved farther away from that beginning, so these two are actually now farther from each other. Again, this same spot that used to be this, that now is this and this, and now 2 million years even farther from each other, moving even farther away. Now, when we see these divergent boundaries, we're most often going to be looking for areas that have frequent, shallow, very low magnitude earthquakes and non-explosive volcano activity. It's mild, they're gentle, they do exist. We will have earthquakes, we will have volcanoes, but they're going to be very, very mellow, not very destructive. So here's a great example. This is the United States, this is Europe, Spain, Africa. So this is our mid-Atlantic ridge that was formed because this plate is moving that way and that plate is moving that way. And you can see we've had tons of just really gentle earthquakes. All these red dots here represent earthquakes that we have seen in that ridge, but they're very, very mild. Same with Africa. You can see this is the Rift Valley in this area, and tons, all those red dots represent tons of just very mild earthquakes. You can also see that the Red Sea, this has gotten much larger over time. These two continents used to be right next to each other, but because of that spreading, this continent's moving in that direction, this one's moving in that direction, so this is going to get larger as well. Now, we can't forget, though, in these areas, I'm creating new areas of continent as these spread. So I'm creating new areas where the magma comes in and spreads with our seafloor spreading. But we have to remember that our Earth can't just get bigger. So somewhere else, that plate is getting smaller. And that is what's happening in our subduction zones, where the plate is pushing this way and then it's going to line up with another one and then it's going to push under. So if one area is growing, like we have in ridges, that means one area is getting smaller. All right, these sinking regions are known as subduction zones. They occur in the ocean, and sometimes we'll see it with continent to continent, but primarily in the ocean because this ocean crust is so thin. And we're going to get trenches when this happens in the seafloor, where all of a sudden our depth is going from like 5,000 all the way down to 11,000 meters. So wherever this trench is going to be very, very, very deep, and that is a sign of this subduction.
Subduction means that one plate is going underneath the opposite plate. So you can see an example here of this plate. When it meets this plate here, it's going to go under.
So in the Pacific here, you can actually see it. These are all trenches, this whole area. And this is where the Pacific plate is going underneath these continental plates over here. So you've got massive, large trenches. We also have lots of volcanoes in this area, and we have lots of earthquakes. So they kind of go together.
Right, so when our lithosphere and our crust drops down beneath another plate, we're carrying a lot of rock and material. So that when that heads down into the mantle, it's going to melt. But it's going to melt with all this water trapped in it. That is what goes up to create very powerful volcanoes. So it's when we have these rocks that are combined with water that go into the mantle and they melt, they're going to cause the very, very powerful volcanoes here.
In addition, we're also going to get very powerful earthquakes. Look at this. These are all some of the earthquakes that have happened, even down to 700 kilometers below the surface. That's massive. And those deeper earthquakes are more powerful. So remember, subduction zone, we're talking about powerful earthquakes and also more powerful volcanoes as well. So when the plate goes underneath, we're going to get a trench. But parallel to those trenches, we're going to have very powerful volcanoes. And that, again, is due to that melting crust that's combined with water that rises up to create a volcano and a very explosive one. Now, we're right now just looking at ocean to ocean, but this can also happen ocean to continent as well. So our ocean crust is going to hit the continent. It's going to go lower, melt, creating volcanoes again. And because we're taking that wet seafloor rock, these are going to be explosive volcanoes. And we're also going to get tons of mountains. So it's like a volcanic arc. They call these folded mountains. These mountains are massive. So a great example of this are the Andes Mountains in Chile. Huge, right on the coast, because they've folded up with the land due to the subduction, and there's always tons and tons of volcanoes. So very tall and lots of volcanoes. Just another way I'm going to show you this and just re-emphasize this point. So we have our ocean lithosphere. It comes down, it melts, creating our volcanoes. So we should be looking for volcanoes about 100 kilometers to 300 kilometers away from the trench. That's a very common theme that happens. You can actually see it here. Here's the trench, and now here are your volcanoes. Japan's known for tons of volcanoes. So same thing that's happening. I also wanted to show you, again, we're getting these deep, deep, deep earthquakes that are happening. So things to just keep in mind whenever we have these subduction zones, we're looking for volcanoes about 100 to 300 kilometers away from the trench. These volcanoes are going to be powerful, and when we have earthquakes, they're also going to be deep and powerful.
Now, as I mentioned before, the crust is composed of these 14 tectonic plates. The interior very rarely has earthquakes or volcanoes. We're going to talk about one example to this with Yellowstone a little bit later, but most of this volcanic and seismic activity is going to happen on the boundaries, in between the plates, especially around the Ring of Fire, which is around the Pacific Ocean.
So here you can see our areas where we have subduction and where we have other plate interactions. The larger volcanoes, as I mentioned, are happening on the subduction. So it's all around the Ring of Fire, tons of subduction, where we're getting deep earthquakes. And same on the other side of the U.S. and down along South America as well. So a lot more deeper earthquakes where we have those subduction zones. Other areas, we could have plates coming together or they're coming apart. So you're going to have a few, but not nearly to the depth that you do at subduction zones. And then as I mentioned before with the volcanoes, we do have volcanoes all around the world, but they're most common in these areas of subduction. So the Pacific Plate, the Ring of Fire, because the activity happening with this plate moving, subducting under these other plates, it's moving at a very, very fast rate, causing this extreme activity in this part of the world.
All right, let's talk about these boundaries here. So we have divergent, convergent, and transform boundaries. Let's look at some. We've talked about divergent boundaries already. These are where we have plates moving away from each other. And we mentioned before, when this happens, we're going to get ridges, mid-ocean ridges. We're going to get rift valleys. We're going to get mild volcanoes, weak, shallow earthquakes. Then we have convergent boundaries. These are areas where the plates are moving towards each other. And one moves towards the other, one of them is unfortunately going to have to subduct underneath. So when we have convergent boundaries, we're going to have trenches, ocean trenches, islands, our folded mountains, and very explosive volcanoes, deep, powerful earthquakes.
Now, we mentioned before there are three types. I think I've talked about two of them so far. So sometimes we have ocean, pretty simple. Then we have ocean continent, where we're going to get these folded mountains right here. But then we actually have continent. Continent's really tricky because there's not a lot of room for one to fold under the other. So they're really just pushing at each other. And it causes these mountains here to get really, really tall. So your example would be the Himalayas. That is your example. So the Himalayas are a continent-continent convergence boundary. And then finally, we have transform boundaries. There's not a ton of examples of these. The best example, however, is the San Andreas Fault. I highly recommend, if you've ever lived in California or you've been dying to move there, this is a fascinating area. It's very visual. And people have put fences that go across this, and over time, their fence posts move farther apart from each other. No volcanic activity. It's kind of some powerful but shallow earthquakes. But at the end of the day, what's happening with these, which is so unique, is I've got one plate moving that way, another plate moving that direction. So these two plates are just sliding against each other.
All right, now we're talking about hotspots. I think hotspots are actually fascinating. This is how the Hawaiian Islands were formed, but they're going to form in the middle of tectonic plates, where I have this like plume of very, very hot mantle that's going to punch through the crust. So here's an example here. This area just happens to be super, super hot mantle. And we're going to get just a powerful punch every once in a while that punches through the crust, and it creates an island from there. But then over time, the Pacific plate is moving in that direction. So the next time one of these happens, my other islands have already moved away. And now we're going to punch through and a new island is created. So Kauai was one of our first original islands. It used to be here, and over time, the Pacific plate has moved it in that direction. And that is how we have gotten the rest of the islands like Maui, Hawaii, and so. So right now, Mauna Loa is extremely active, but we also have new islands forming as this whole chain moves in this direction here.
So you can see that originally the hotspot is probably right around in this area, right here. And Kauai is 5 million years old. Oahu is 3 million years old. Molokai, 1.8 million. Maui, and then Hawaii is only 400,000 years old. So these islands have all moved in this direction. Eventually, the Hawaii island will also move, and a new island will be created right here. Now, on land, there is one example of this right now. There's actually a hot spot in Yellowstone National Park in the middle of the United States. So it's just very interesting. We're all watching to see what happens there. But there's a lot of geological activity in that area, a lot of geothermal springs because of that hot spot that does exist. AP wants to make sure that you know these symbols, because there could be times where on the exam you're given a map and you need to know what these symbols are and how they relate to the different boundaries. So 2-line is just a divergent. A line with these little like triangle bumps is a convergent. And most important, the line of these, the way the triangles are pointed, that's the area of the subducting crust. And our transform has arrows headed in different directions. Very self-explanatory.
All right, so I want to remind you that all of these dots here represent geological events. And we have to remind ourselves that these have major consequences into the environment. So every time one of these happens, it can have a large impact on the environment around it, especially when we have earthquakes. Tsunamis are formed due to an underwater earthquake. So the crust here is going to all of a sudden just break and shift, and that's going to release a lot of energy. This increase here is going to create more energy and create waves that are going to crash when they hit the continent. Some major environmental consequences here. They're going to destroy habitat. They're going to drown species. They're going to uproot trees, contaminate fresh water with salt water and debris. So this has a large natural disruption on an ecosystem that may currently exist. And there could be a lot of consequences on that population or on multiple populations due to that. So we can't forget that. All right, that was a long one, so much information, but thank you guys for sticking with me.